today will be introduced by Logan Ramirez, class of 2001. Logan is a director on the San Antonio Alumni Chapter Board and is an analyst at Secure Logics. Logan?
Good afternoon, everybody. Thank you for weathering out the weather. Coming to join us here on behalf of the San Antonio Alumni Chapter here. Welcome you again. So I get the privilege here of introducing Paul Myers, a native San Antonian, as am I. He's been at Trinity for 28 years, which would have made me 5 when he started. Taking a shot at you there. He's now chair of the computer science department, and during that time has consumed a lot of food for thought himself. He began his academic studies in physics and English and moved on to mathematics, in which he received a BA and MS degrees. After a decade-long career in Colorado State bureaucracy, he then returned to the University of Denver in computer science, where he received a PhD in 1986. And he was one of the students of Ronald Prather, who later became distinguished professor here. In addition to teaching and scholarship, Paul hosted an international symposium on constructivity in computer science. He's published and presented extensively on CS curricular matters, matters such as computer literacy, mathematics and logic in the CS curriculum, and mentoring women students. He has been very involved in curricular changes at the department and university levels, and he's performed major program reviews at 2 American colleges. He's served twice as president of the Consortium for Computing in Small Colleges, CCSC, and as board member of the ACM Special Interest Group on CS Education, where he's published, presented, served on panels, and was a member of an annual symposium planning committee. Paul's non-work life is consumed by too many interests: music, chess, climbing, being a serious couch potato, network TV, Scottish single malts, which is another thing we have in common, ghost stories, model railroading, trap and ski, reptiles. To add more would become even more embarrassing than this list already is. Though he proudly states for quite a few years now he has returned to English and has been taking 1, sometimes 2 classes each semester. By now, he's taken more English seminars than most English majors. This semester, he's reading Joyce's Ulysses for the 4th time. It's my proud honor to introduce one of my favorite professors while I was here, Paul Myers.
Thank you all for coming. What an honor to be asked to make a presentation like this. And what a treat to see Logan. He came up and said, "Do you remember me?" And I remembered him exactly. In fact, he's an example I use for sometimes when I want to make a point at his expense. But actually, it's a favorable reference. Anyway, I might as well just go ahead and get started. I can already see that it's off to a bad start. This is not a breakfast. So there's mistake number 1. I thought I had corrected that slide. So what else do I think I have done in here to improve it and actually not? We'll see. Well, we'll start off with the very first sentence here. It's a lie. Oops, I guess it'd be good if you could see it. I am the only person in this room who knows what computer science is. I can't tell you how many times I've said that in large groups of PhDs and so forth here at Trinity where it's been true. Unfortunately, today it's not true. Damn it, Logan. But well, not only Logan, but Rob and Amy and a whole bunch of other people here who do understand what computer science is. So if you take out about 10 people, well, no, there's Matt, and oh my God. If we remove about half of you, then I think I can say this, that I'm the only person in the room who knows what computer science is. The reason I want to mention that is I have a picture here. It's one of a whopping 2 graphics in this presentation of the Tower of Babel. And I, for quite a long time, have really thought, in fact, this is really probably my main food for thought, so to speak, in this talk, is I have for a long time thought that the phenomenon of the Tower of Babel is not so much having to do with human languages, but with the splitting up of human knowledge into disciplines. The disciplines don't know each other. They don't understand each other. And you get all kinds of really strange things happening. People will come up to me and say, I'm having trouble with Microsoft Excel or something. I guess I know what Excel is. I don't know. I can't install a computer or anything. In fact, I will boldly say that at least half of you use the computer in more sophisticated ways than I do. I send email, I write a memo now and then, and I buy things on eBay. What else is there? A bunch of you are using it in very sophisticated ways. Okay, occasionally I'll open a spreadsheet and put some numbers in, but in a very unsophisticated way. That's not what it means to be a computer scientist, is to be familiar with all of those tools. So I think that this Tower of Babel phenomenon extends to all the disciplines. I mean, it sounds kind of arrogant and audacious for me to say I'm the only person who knows computer science, but any of you could stand up and say the very same thing about your own field. I can only imagine how many times English professors get asked to look over a cover letter, a resume or something, as if an English professor knows spelling any better than anybody else. They don't. That's not what English is. Or a mathematician might be asked to look at a tax return. Could you look this over and check? Mathematicians probably make at least as many arithmetic errors as anybody else. That's not what mathematics is. But we all think we know what these fields are, and we think we're approaching the right people for this, and it's just not right. To get this back to this talk, though, I will say that though I believe this phenomenon is universal, I think that it hits computer science particularly hard, because everybody knows what a computer is, and they think that computer science must be the study of the computer. And then my less generous colleagues will go, a discipline devoted to the study of a tool? And I'm chair of the department, and I buy things on eBay. That's my use of the thing as a tool. Computer science is much, much richer than that, and I want to give you just a little tiny aspect of what a little bit of computer science thinking will do. And Dijkstra was considered one of the premier computer scientists of the world. He was somebody that UT Austin bought, when they were buying their way to greatness. And he came and lived the rest of his life at UT Austin, next to the Gutenberg Bible. And he's famously quoted as saying that computer science is no more about computers than astronomy is about telescopes. And of course, astronomers use telescopes. Sure, most computer scientists except me use computers. Sure, but it's not what it's about. Okay, moving on. There are many ways to think about what computer science is about, and this is one of them. Computer science is about problem solving. But guess what? Every discipline solves problems. I mean, what's so unique about that? But in computer science, we actually study the nature of problems and problem solving, which, other disciplines have their problems, they try and solve them, but we study the fundamental nature of what it means to be a problem and a solution to a problem, and the resources needed to solve problems, and also we worry about the design of solutions, of course. And today's topic is going to deal with kind of the middle one, the resources. It's an area called computational complexity. So let's start by, it's food for thought, so I don't feel ashamed of asking you all to do some math. Let's start with a common grade school problem, multiplying two numbers. The first one, we multiply 5 times 3, and we just dig out of our brain that that's 15. 37 times 45 is a little bit more complicated, and we have to do a little work. We have to multiply 5 times 7, and then 5 times 3, then 4 times 7, and 4 times 3 to get these two numbers, and then at the end we have to add. Okay, then we get these two numbers. This is even more work. 7 times 8, 7 times 5, 7 times 4. Then shift over, 3 times 8, 3 times 5, 3 times 4. Then shift over, 5 times 8, 5 times 5, 5 times 4. And then do a little adding at the end. Gets kind of tedious. Probably the largest two numbers that you ever multiply were like 4-digit numbers or something. And I'm not even sure I ever did that. Obviously, these get more tedious, but can we predict that? Can we talk about this tediousness in a way that's predictable? For example, we would much rather do the multiplication on the left than the multiplication on the right. But why? What about those numbers allows us to predict that one multiplication will be a nuisance, the other will be a bad dream? Well, let's explore that. Why can we predict, before we even carry it out, that the left one's going to be so much easier than the right one? Something becomes immediately apparent. The amount of time, the number of steps, grows as the size of the numbers, which we speak about algorithms in computer science, and algorithms take inputs and they produce outputs. They take things to work on and they produce answers. So in computer science, we'll often use the word input, of course. So as the size of the numbers grow, we will, it'll get more complicated. And so what I've done in this table below, taking those same numbers from a previous slide, was looked at the size of the numbers. Now, we get to do a big simplification. The size of the numbers, I'm not taking 458 to be size 458. I'm taking it to be size 3. It only has 3 digits, and that turns out to be the crucial thing. That's why we could look at those previous two. One was 2 3-digit numbers, the other was 2 10-digit numbers. We didn't have to care how big those numbers were, except for how long they were, how many digits they were. And that's where he said, no, if he assigns that second one, I'm just leaving the lunch. I'm not going to do it. So let's look at the 3 examples there. The first one, the size of the number of digits is 1 for each of the numbers. So there's 1 multiplication and no additions. So a total of 1 step. Remember, we're talking about resources or time or steps here. The second one, each number has 2 digits. So we'll say that the size is 2. The number of multiplications is 5 times 7, 5 times 3. 4 times 7, 4 times 3. And there's 4 of them. And then we do 4 additions at the end. The next one, 3, remember, we went through this. I'm not going to go through it again. 7 times 8, 7 times 5, 7 times 4. That's 3, but then we do it for each of those 3 bottom numbers. So we get 9 and 6 additions for a total of 15 steps. I'll just tell you that if we had 2 4-digit numbers, it would be 16 multiplications and 8 additions. But now, in the spirit of interaction and multidisciplinarity and everything else, I'm going to ask you, if I gave you 2 10-digit numbers, which is those ones on the previous page were 10-digit numbers, and ask you to multiply them, I'll tell you that when we're all said and done, it'll be 20 additions. But how many multiplications will it be? 100. 100. See how easy this is? So that's exactly it, because each of the 10 has to multiply each of the other 10. So this leads us to a function, remembering back to your high school and college days when we had functions, a function t of n. How many of us would relish the prospect of multiplying 2 10-digit numbers? That we already decided that would take 100 multiplications. How about 2 100-digit numbers? That multiplying 100 by 100, we would get 10,000 multiplications that would have to be done. In general, then, for inputs of size n, and that's what we, remember, part of the object here is to predict, to be able to look at, say, these 2 numbers and predict how much work we're going to do. Well, we can't just say size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because we don't know. Something could come in at size 100. Something could come in at size 1,500. We don't know. So we use a variable called n. So let's just say that the size is n. So in general, then, for inputs of size n, which the size n stands for the number of digits. So 457, n is 3 digits. Our multiplication algorithm or method or technique requires n squared multiplications. That is n times n. When you all answered 10 digits times 10 digits, that's 100 digits. 10 times 10, 10 squared. and about 2n additions. I don't want to talk much about additions, but that's how it works out because of that shifting to the left. So you get the 10, but it shifts to the left one time each time, and so it's another 10, and so it's about 2n there. So we say that our old grade school algorithm, which we all learned in grade school and maybe use occasionally even now for multiplications, has time complexity, T of n, time complexity based on the size n, equal to n squared plus 2n, where n is the size of the inputs. Here it's merely the length or the number of digits. But in general, when we talk about the complexity of an algorithm, we talk about the size could be anything, not just number of digits, because sometimes we don't just work with numbers. This leads us in the field to talk about orders of magnitude, which is a concept from mathematics, of course, that only the most significant numbers we're interested in. We're not interested in the fine-grained detail. So that, for instance, given what we were just talking about, n squared multiplications, if we have 100, we'll have to do 10,000 multiplications. If we have 1,000, we'll have to do 1,000,000 multiplications. If we have 10,000, we'll have to do 100 million multiplications using our grade school algorithm. And then the total steps, what you find is the number of additions keeps growing also, but as a percentage of the total, it becomes less and less significant. At size 100, there's only 200 additions, so that's only 2% of the total number of steps. At 1,000,000 multiplications, it's only 0.2%. And at 100 million multiplications, even though it's 20,000, that 20,000 is only 0.02% of the total steps. So we actually, the function is n squared plus 2n, but we don't care about getting it that precise. So our algorithm working on inputs of size n takes n squared multiplications, plus I'm happy to say, and in computer science we're happy to say, plus a few additions. We don't care. It doesn't add that much. Thus, the term n squared dominates the overall complexity of the whole complexity function, n squared plus 2n. So we say that the complexity, T of n is equal to n squared plus 2n, is of order of magnitude n squared. We just throw out the 2n additions. We don't care. It doesn't bother us. So we say T of n is big O of n squared, and that's how we call it, big O. It just means order of magnitude. If you really want to impress some of your computing friends, tell them that you know big O of grade school multiplication. It's big O n squared. And I guarantee you, depending on your friends, you'll have them sitting in a hurry. I mean, this is something we don't get into with our own students until sometimes their sophomore, junior year. Well, this big O, it matters. And that's where we're going to get to kind of the next phase of this talk. This was just kind of a little technical background using an old algorithm, an old procedure, a method that you've known since 4th grade, I guess. We've all known it since 4th grade. How do you multiply two numbers? And we, without necessarily knowing why, we all knew that, damn it, if they ever assign two 5-digit numbers, I'm transferring classes. You know, I don't want to do 25 multiplications. So I think the highest they ever gave us was 2 3-digit numbers, and we hated those enough. So now let's do something unusual for a talk from the chair of a computer science department. Let's talk briefly about computers, as much as I hate to. Nowadays, an operating speed of 1 or more gigahertz is quite usual. That is about 1 billion or more operations per second. Incredible. Again, multiplying two 10-digit numbers, order 10 squared would be about 100 steps, more or less, because we threw out the addition, so I'm just going to say more or less, about 100 steps. This would ruin our afternoon. We wouldn't want to do it if we had to do it by hand. But a modern computer can do 100 steps in less than a blink of an eye. You know, if it can do 1 billion operations in a second, then those 100 steps, no, just not very problematic for a computer. In fact, two 1,000-digit numbers will take about 1,000,000 steps, as you and I already determined. N squared, where n is 1,000, that would be 1,000,000. Enough to ruin our week if somebody asked us to do that. A computer could do this easily in less than a second. But note here, and this is important, in either case, human or computer, our grade school algorithm takes about 1,000,000 steps. There's nothing magical about the computer that it can I just know the answer. No, it has to do the steps. And if it uses that algorithm, it has to do 1,000,000 steps. Just like we have to do with a piece of paper and pencil. It's just, it can do it a bit faster. That's the only advantage we get from the computer. It's the same method, the same procedure that's being used. Okay, now let's look at something a little more fun. No one really ever got off on grade school multiplication. Another example, which we'll call the traveling salesperson problem. We can easily compute the complexity for any algorithm. If you can write a methodology to solve a problem, we can compute the complexity of it. An algorithm being a set of instructions for human or machine. The purpose of the last slide was to try and convince you that there's nothing magic or strange or different about the computer except its speed. It's insane speed, which of course is magical and different and so forth, but it's just a matter of speed. The traveling salesperson problem. We want to visit each of a certain number of cities, say n of them, in the shortest possible trip, returning to start. Well, I can't readily think of an efficient method or algorithm to do this. I just doesn't come to mind. But I can certainly think of what we call an exhaustive search or a brute force algorithm that is pretty trivial. All we would do is we would just list all the routes, all of the conceivable routes, and then for each route we'd look and see how many miles or whatever they took, and pick the one that's the shortest. Okay, I mean, kind of straightforward, kind of mindless approach to this. You know, be like if you wanted to talk to somebody else in the room, rather than just go over and talk to them, you work your way through every single person until you finally get to them. Kind of inefficient, but it works. Usually we have a more direct way of solving a problem, but I'm not going to worry about a more direct way. I can't think of one right at the moment, so I'm just going to go with the brute force, exhaustive search. Just keep chugging them out and find the shortest one. Well, that's easy enough, I would claim. So let's look at a situation where we've got 4 cities, and this is my big attempt to include graphics. Some of you, I think, thought, yeah, right, he's chair of the Department of Computer Science. I know more about computers than he does. Here's my proof. It is color. That was an accident. It just came with color. The tool that I pulled out and drew these lines, they were blue, yay. So anyway, so here's an example of the traveling salesperson, some routes. How many routes are there to check? Well, let's say that n is 4. We've got 4 cities, A, B, C, and D. Well, this gets a little mathematical here, but really not much. We have 4 possibilities to start. We can either start at A, B, C, or D. And here, we'll either start at A, and we don't know the next 3 we're going to visit. We'll start at B, we don't know the next 3, C the next 3, and D the next 3. So we have 4 possibilities to start this tour of all the cities. After we choose start, we then have 3 possibilities for the next city. For instance, if we've chosen A, which I've underlined, we could next go to B, or go to C, or go to D. If we're trying to get all the routes. Remember, this is exhaustive. This is brute force. This is going through and talking to every single person in here to find the person we're looking for. Stupid algorithm, but it's guaranteed to work. So we'll do that. And then similarly, for B, we have 3 choices. For C, we have 3 choices. For D, we have 3 choices. And then, of course, XX, because we don't know where the next ones are going to be. So notice our 4 cities have now expanded up to 12. 12 because of this, the way this works. I'm going to repeat that exact last thing on this slide. So from the last slide, this is exactly the same table, 4 times 3. Now for each of these 12 cities, we have 2 possibilities for the third city visited. So for instance, if we looked at AD as one of the AD right here, we've got 2 possibilities. We can do ADC or ADB. And of course, once we do ADC, we only have one choice for the next one. It's going to be B. And if we do ADB, we only have one choice for the next one. It's going to be C. So I'm just going to combine both those here. And here is ADBC, ADCB. But then here it is done for AB, AC, AD, BA, BC, BD, so forth and so on. Well, we started with our 4, which are up here now. I can see them, but you can't. Down here, we have 3 choices for each of the 4, so that's 4 times 3. Here we had 2 choices for each of the 4 times 3, so 4 times 3 times 2, and I just went ahead, instead of putting x's in the last position, I just went ahead and put the one it had to be. So we got 4 times 3 times 2 times 1, which is 24 possible routes. We now look at all the different mileages on all of those 24 routes. One of them is going to be shorter than the others. We have the computer say that's the shortest route that connects all 4 cities. Computer can do over 1 billion operations a second. Oh, I got to say that in public. Over 1 billion. I can't do it. It sounded like Carl Sagan initially, but now I can't do it again. Billions and billion, whatever. So a computer can do over 1 billion operations in a second. We've got a whopping 24 routes, so the computer can whip that out again faster than you can blink your eye and give you the shortest route. The title of this slide is exclamation point. So there are 4 times 3 times 2 times 1, which is equal to 24 possible routes to check to find the shortest. For those of you who remember some high school, college math, you'll know that 4 times 3 times 2 times 1 equals 4. Oh wait, wrong use of the exclamation point. It's called 4 factorial. How many people remember that from grade school, or high school or something? It's called 4 factorial. It's just a shorthand. Excuse me, if you want to do 5 exclamation point, that's 5 factorial, and it just means you multiply 5 times 4 times 3 times 2 times 1. You want to do 10 factorial, it's 10 times 9 times 8 times 7 times 6 times 4, times 5 times 4 times 3 times 2 times 1. I think I'm up to at least 3 mistakes now. You're not getting your money's worth, folks. So in general then, if n is the number of cities, there will be n factorial routes to check. Well, let's consider a mere 50 cities, just say the state capitals of the United States. We're not even talking about all cities in the world of population over 250,000 or something like that. Or not even all cities in all county seats in the United States. That'd be a really big number. We're just going to look at the state capitals and see if we can find the shortest tour to do all the state capitals. Part of me would be tempted to ask some of you to pull out your smartphone and figure this out. But the title of this, we'll put something in front of the exclamation point. The title of this slide is 50 factorial. That's how many routes there would be to check. 50 factorial is approximately 3 times 10 to the 64th. That means 3 followed by 64 zeros. What does that look like? It looks like that. That's a lot of routes. Talk about ruining your weekend. So there's that many routes to check. To try and get it all in one line, I can reduce the font substantially. And for some of you in the back, it's just a blur of zeros, this little sea of zeros. That's how many routes there are to check in my little brute force common sense algorithm to do. If we had a computer that could check a quadrillion, which I looked it up on Wikipedia, it's a million billion. If we had a computer that could check a quadrillion routes per second, and let me just say that we're nowhere close to that kind of technology. I don't think anyone even dreams of such an incredible speed on a computer at this point. We can right now do a few billion operations per second. This is over 1,000,000 billion operations per second. We're nowhere close to that. It would take that many seconds. Notice it's a smaller number. I whacked off a bunch of zeros, like 15 of them or something, because we're doing that many a second on a computer that no one predicts will ever exist. This works out to be more than, I went ahead and put in the commas there so you got a real feel for this number, right? Like we have a name for such a number. We don't. There's no name for this number. It's so big. 3 times 10 to the 40th years to get all of the roots listed and compare them as to which one is the shortest. By the way, that's far longer than the universe has existed, which is estimated at 14, followed by a pitiful 9 zeros years. This is followed by 40 zeros years. So we would need a lot of universes to figure out how the shortest route is for the 50 state capitals of the United States. It seems like something you might want to do sometime, get in your airplane and go visit each guy. You want to save fuel, you want to save time and so forth. You want to do the shortest possible route. Well, if you've got this much time to wait, if you can go into suspended animation for about the life of a trillion universes, you could wait and get that exact shortest route. This is me trying to do a weird little graphic thing. I found a font that has what looks like an alien face, and I found this big, nasty, dark X, so that's supposed to be a skull and crossbones. Yay. Very exciting when I discovered that. Okay, so I don't even know how we're doing on time, but I think I'm going to finish much sooner than I needed to. But they said maybe there's questions and answers. I still got some more to say, though. Never fear. I keep looking for my iPhone so I can look at the time. 12:44. Yeah, we're doing good. They said I should finish by 1. They. You know who they are. So here's a little epilogue to the traveling salesperson problem. While we can readily come up with an algorithm to solve the traveling salesperson problem, I explained we just add up all the roots. Who has the time to wait for the answer once the number of cities goes beyond about 20? Once it goes beyond about 20, we're already talking about years of this super fast processor to do the work. Sadly, though many have studied the traveling salesperson problem and many others like it, there are a lot of problems out there that are like this in very fundamental ways. No one has found an appreciably faster way to solve it. My little stupid way of let's just look at all the roots and add up the distances and pick the shortest one, that's really hasn't been improved on by much. There's one, and it's one that would probably come to all of our minds. It's called a greedy algorithm. It says wherever you are, like if you're at that little city, instead of coming over to this city, you'll pick up these 2 first. In other words, you'll grab the closest. Wherever you are, you'll grab the closest cities. That seems to make a lot of common sense. And that greedy algorithm does help. But believe it or not, there are situations where it's better to run first and get one that's far away. Like let's say all the closer ones were way over there receding out into the distance. It's better actually to go pick this one up first and then go do your little close ones. So that when you get way out there by the statue, you don't have to come all the way back and grab this one. So, the greedy algorithm is easy to trick, but the greedy algorithm or some modification of it will get us within about 30% of the optimum solution. And this is kind of an interesting thing, that we can actually prove that. We can prove that the greedy algorithm gets within about 50% of the optimum solution, even though we don't know what that optimum solution is. This, folks, is computer science. This is what we do in computer science. And I'll mention that most experts suspect, and I mean very high-powered experts, suspect with very good mathematical evidence that there will never be a significantly faster method. The problem is in a class of problems that we call NP-complete, that are considered to be actually intractable. Intractable, without giving a formal definition, basically means we can write algorithms for them, we can write methods and procedures to solve them, but universes haven't lived long enough for those algorithms to run their course. When you get to an N of size, reasonable size, 20, 50, 100, which for real world problems is really small. Like I said, visiting the cities, why just the state capitals? Maybe I want to visit all the county seats or something like that. And I'll just mention that many of these problems, alas, are of economic, commercial, and military importance. These are important problems. Imagine you're in the airline delivery business or something, delivering packages. Since the best known algorithm only gets us within 30% of optimum, if you can find a shorter route, you've got an advantage over your competitors. That 30, if you can get yours down to 20%, then, many flights a day, 7 days a week, 365 days a year, blah, blah, blah. All the fuel, the personnel, the airplane maintenance and everything really adds up. I mean, these are not trivial, long-haired problems or something. These are very practical problems, many of them. Okay, some sort of final notes here, which of course, there's one more slide after this. But what would that be, mistake like 80 at this point? 80 factorial or something? So some final notes. I have to tell you a friend's reaction. He's not in the room, but I'm not going to mention his name anyway. One time we were hanging out, and he just said, "Paul, tell me something interesting about your field." Well, what's more interesting than this? I mean, seriously, you've been to a lot of food for thought luncheons. What has been more interesting than this? I mean, good God. So I said, well, okay, let me tell you about this traveling salesperson problem and stuff. Pulled out some napkins, because of course all mathematics is done on napkins. And we worked it out at the table. And so at the end, he's just dazzled, which of course he should be, which of course all of you should be. Like, whoa, will my head stop reeling? I don't know the answer to that question. But he was definitely staggered by this. He thought about it very carefully as I was saying it. His reaction was, oh my God, Paul, I had no idea that computers were so limited. Thank God we could just pull out a map and a ruler and a piece of paper and just do it. Oh, I think maybe I wasn't very clear about something. If we take those 40 zeros as to how long a computer would do it, and you want to do it by hand, we can throw back in about 30 more zeros as you do your little additions of all the distances between all the state capitals and everything. That's why I didn't make that mistake here. I started with grade school multiplication to give you an idea that the computer is doing exactly the same things you do when you multiply two numbers. It's much faster. That's the only difference. So my colleague just thought this has to, and what it really boiled down to was that his mind could not accept that such a trivial problem was so massively intractable and virtually impossible. His mind couldn't cope with that. And so he had to blame it on the computer, thinking, oh, there must be some fundamental problem with computers. But in fact, the computer, all it adds to the equation is speed. That's all it adds, is speed. So my friend had it exactly backwards. I don't think he killed himself, but... So... Yeah, right. Yeah, right. He said he's still driving around. Yeah. a somewhat new view, and this is kind of a new view of thinking about things. It's not Aristotelian necessarily, or medieval or Renaissance or something. And the computer's been instrumental in this because we can suddenly model on the computer, because of its insane speed, things that to try and do them by hand or by equation were never approachable by mathematicians or engineers or anybody else. So there's somewhat a new view that has come to be because of computer science, that some phenomena are so complex that the only way or most efficient way to predict their behavior is to just let them run their course. You know, you can't, they're too complex to get in there and model and figure out, okay, if we start this going, here's where it will end up. It's actually more efficient to just start it going and see where it ends up. One of my favorite quotes of all time that I forgot to write down the attribution, and I have looked and looked and looked, and I've asked and asked and asked, and no one has been able to find it, but it was something like this: in a sufficiently complex system, never proceed any maneuver by a comment more predictive than "watch this." I love that quote. And another little story to kind of bookend my story with my friend. The Coast Guard once approached MIT with a request to find the shortest route among a bunch of buoys in the Chesapeake Bay. A person had to go out in a motorboat a couple times a day to take water samples, monitor temperatures, etc., at each of these buoy sites. Over time, having the best route would save considerable money for fuel, boat repair, maintenance, overtime costs, etc., real economic impact. The MIT people said they'd be happy to help, but how many buoys had to be visited on each trip? 300. A mathematical pun. I mean 300, I mean like 300. But now what you all know is we actually use that exclamation point to mean 300 factorial. If 50 factorial already took 10 to the 40th years to compute, 300 factorial? Ugh. Okay, the title of this talk, if you remember back there, and you're probably thinking, this is mistake number 5 or 6, he called it the sorrows and joys of complexity. I don't see any reason to be joyful. Well, look at me. I get to make a career out of studying these cool things. Now, if that isn't joy-producing, what is? Oh yeah, so what if your companies fail and all that kind of stuff because you can't get the shortest route and stuff? I get to have fun. So, no, that's not what I meant by joy. I'm not that mean. There is a silver lining to all of this, and it might not be instantly apparent, but I want to just take my last couple minutes to talk about it. But this is the last slide. There is we have the silver lining to this immense problem of these intractable problems, NP completeness we call it. I mean, it's awful. It's awful that we can't give companies and Coast Guards and stuff like that the information they need to most efficiently do their job. And it's just awful that as theoreticians we can't figure these things out. But where in the world did cryptography come from? Well, that would be a whole nother series of lectures and stuff like that. But let me just say that if every problem were tractable, if every problem were easy to solve, then there'd be no way to do cryptography. Because whatever you would do to encrypt some information, a hacker could easily penetrate it, easily solve it, if every problem were easy. So you may never have thought about it quite this way, but the whole basis of cryptography and secure passwords and so forth is based on the fact that the problem involved in cracking that cryptogram or that password should be intractable. That, you know, it should take, if you've got a robust password, it should be the case that the best algorithm to do it is a brute force algorithm that will take many years to find your password. That's what we're talking about, computational complexity being more or less intractable. So what looked like all through this lecture toward the end, as just the worst news you've ever heard about the capabilities of the human mind and stuff is exactly what allows cryptography to work. The fact that there are immensely difficult problems that someone can't just sit down and take a few hours and crack it. So given that we live in an environment where there are, yes, bad people, cryptography is very necessary. I mean, we need to keep our privacy. We need to keep our money in our account and so forth and so on. So that I regard this as a really substantial silver lining to this problem of this immense difficulty of solving certain problems. And I guess that's it. So, I mean, I'm happy to answer questions or anything. Thank you. Thank you very much. Like I said, it's such an honor to be here. It was such a thrill. And I had so much more fun doing this than I thought I was going to. Yes. Oh, now the fun's going to stop. There's going to be hard questions. Oh, those are the hardest.
You know, in that movie, Rain Man, remember when Dustin Hoffman could do those numbers? Is it possible for a savant to do that?
Well, that's an interesting question, but it's too silly to answer. Next.
I wish I could get that.
No, that is a really interesting question. I can't say that I've thought about it, but my guess is that that kind of savant behavior is not exactly mystical. It's not like the number communicates something about itself to you. There's still got to be processes going on. Excuse me. And those processes, you know, this would be an interesting experiment. I think I can predict the outcome. If you gave a savant who, say, could multiply two numbers, you gave them 2 3-digit numbers, and they just give you the answer like that. My guess is that if you gave them 2 100-digit numbers, it would sort of slow them down. Maybe to the point where they wouldn't be able to even do it. Now, this is speculation, but that would be my strong guess, is that still, even doing whatever they're doing with lightning fast rapidity in their brain, is still going to be slowed down as the size of the inputs gets larger and larger and larger.
You talked about brute force.
Mm-hmm.
By adding some complexity, don't we decrease some of the processing time, like conditional logic? Some if-thens in there that...
Well, yeah, I mean, even doing the brute force is going to have a lot of contingencies and logic and stuff like that, because even doing the brute force, you've got to make sure that you don't revisit a city on the route. You keep drawing new cities, so you actually have to create a little data structure and put things in it and remove things out, and there'll be iteration based on logic, and so there'll be a lot of logic and all that's going in there. And then I think another aspect to your question is in these kinds of things we talk about heuristics. Like, heuristic is just a fancy word for rule of thumb. Can we just come up with some heuristics? And oftentimes we can. Oftentimes, not every problem is intractable. I mean, I can sort all of you. If I had your last names, I could sort all of our last names in this room very quickly, very quickly. Like, what was there, like, or search. If I had a list of all of you and I was searching for one person, if there's like 70 people in the room, I could find the person I was looking for in less than 10 steps. By using a heuristic, kind of what's called a binary search, as some of you know. And so, like, the example I gave is a heuristic would be, hey, look, why don't we, wherever we are, just go to the shortest possible city, the closest one, before we branch out. And like I say, that heuristic works very, very well, but it doesn't work well enough to solve the problem completely. It just works well to get a not terribly decent approximation. but it saves a heck of a lot of time over, I mean, that kind of heuristic of the greedy algorithm, you took the 50 state capitals, a computer could do that in 1 or 2 seconds. That's the improvement, as opposed to 10 to the 40th years. But it only guarantees you about within 30% of the best possible. Well, that's a good question, too. Both of them have been good questions. I'm waiting for a bad question. Oh, here it comes.
I'm not going to give you a bad question, but as an example of what this does. Back in the 1970s, I was an advisor to 17 Dutch pension funds, and they would have me analyze and purchase properties in the United States. And if they changed the variable of the interest rate, the rent on the property, the tenant change, it would take me a week generally to do one calculation.
When was that?
This was in the 70s.
The 70s.
It would take me a week. And I think it was 78 or 7, around there, VisiCalc came out that Apple Computer had at that time. And my company thought I was crazy. I went out and bought the computer, paid $1,700 for it, paid, I forget what, for VisiCalc. My company, a major company, would not pay for that, and I paid for it on my own.
Wow.
In about 3 days, I learned how to program VisiCalc. I could then put in a variable, and within less than an hour, I could change whatever variable I wanted. And that's the magnitude of 1 week to do the work versus an hour or less, and it got less as I got more experience.
Well, and as computers improve, my guess is now it's a matter of a second or two.
Now it's a matter of seconds. But the company went around and bought everybody a computer.
Right. A point I want to highlight there, I'm glad you raised that real world example, but a point I want to highlight is that, again, the computer was not doing anything fundamentally different than you were doing. It's just it took you, a human being, with a piece of paper and a pencil, a week. The computer could do exactly those same steps in an hour, and now probably in under a second. Anybody else? You're just too staggered, right? Well, again, it's such an honor for me. I really appreciate your all's attention.